Now we are going to discuss about restoring division. It is a technique used for integer division. So we are doing the division by performing the multiple subtractions. For that we are using that adder circuit. This is the circuit arrangement for the binary division. So we have a adder circuit here. Then we have the dividend is stored in the register Q, the divisor is stored in M, then we have a register A. Initially it will be set as 0. Okay. Then depends on the MSB bit of depends on the MSB bit of register A. So the control sequencer decide whether it need to do that subtraction or not. Then so we need to, for every cycle, we need to do that left shift operation among the register Q and A. Then what need to be set in the LSB bit of register Q? It also depends on the value MSB bit of A. Okay, I show you the example. Then we come to the circuit arrangement part again. Then you can easily understand. Okay. So these are the step for restoring division. So first you need to shift register A and Q in the left side for one binary position. After that you have to subtract M from A. So subtract it is equal to A minus M from A. It is for that you can also it is equal to A plus 2's complement of 2's complement of M. Okay. So instead of doing the subtraction, you can add the 2's complement of M with A. Okay. Then store the result back in the A. Then you need to check the sign bit of A. If the sign bit is 1, then set Q0, that is LSB bit of register Q into 0, then add M back to the A. This is called as restore. Okay. Otherwise, if the sign bit of A is 0, set Q0, LSB bit of Q0 1, and no need to do the restore operation. Okay. By using these steps, we need to do the problem. Okay. Now consider this example. So this is the 100. This is the dividend. Okay. Then this is the divisor. Okay. Then we need to perform the division operation. So initially, okay, you need to have a register A. This is the register A as 0. Then register Q is you need to store that dividend value in the register Q. Okay, so this is then you need to store that divisor in the register M. So this is the register A value initially. This is the Q. In Q, I have stored that dividend, that is 1000. Okay. Then this is the register M is having the divisor. Okay. So Q is initially having the dividend, M is having the divisor, A is initialized as 0. So, okay, all the initialization. Okay, this is initialization as over now. Okay, what is the first step? See here. So, you need to do the shift operation between A and Q, that is left shift. So, this is A, this is Q. Do the left shift operation. While doing left shift, this bit comes here, this become empty and this bit will be discarded. So 0, 0, 0, 0. This one is here, this 0, 0, 0, this become empty. What you need to do next? Subtract M from A. Okay, so what is the value of A now? So after shifting, this is the current value of A. So instead of subtracting, already I have told, right? Instead of A minus M, what I do? a is plus 2's complement of m. So I take the 2's complement of m. What is the m value? 0, 0, 0, 1, 1. This is m. What is 1's complement? 1, 1, 1, 0, 0. Then 2's complement, add 1 in the LSB. 1, 0, 1, 1, 1. It is a 2's complement. So this is the 2. I write the 2's complement of m here. Then I am adding the 2. 1 plus 1, that is 10. 0 here. Carry 1. So 1, 1, 1, 1. Okay, clear? This is the 2's complement of m. I am adding this 2's complement of m with, this is the current a value. I am adding this a and 2's complement of m. So I get this result. This is the current a. Now, what you need to do now? See the third step. Sign bit of a is 1. If the sign, you need to check the sign bit. This is the MSB bit is always sign bit. If it is 1, you need to set Q0. After shifting, the Q0 become empty, right? If it is 1, you need to set the Q0 bit as 0. Okay, so I have set it as 0. Then what I need to do? Then add m back to the a, that is restore. So add m value is, the original m value is 0, 0, 0, 1, 1. I am adding that 1, 1 plus 1, 10, 0 here, carry here, again 1 plus 1, 0, 1 plus 1, 10, 0 here, carry. So ignore the carry, is 10, 0 here, I ignore the carry. So this is called as restore operation. For restoring, so I have, as I have subtracted there, for restore I am adding m here. Okay, otherwise you can directly write the original value of a. Okay, that is restoration. As we have overwritten a, we cannot go to the previous stage. Okay, so as I have subtracted here, I am added, for to go to the previous stage, I am adding the value of m. Okay, so I get the previous value of a. Okay, now the first cycle is over. Okay, the 3 step has been over. What you need to do? Go to the second cycle now. Okay, again, the first step is shift. I am doing the shift operation. Okay, while I am shifting, so the shift is happening among A and Q. So while shifting, this bit comes here, this bit goes here. I discard this. Okay, after shifting, this is my value. Then what I need to do, the second step is subtract a minus m. Instead of a minus m, this is the, I am adding 2's complement of m. So I am adding that. So this, after adding, this is the result. So 0 plus 1, 1, 1 plus 0, 1, 1, 0 plus 1, 1, 1. Okay. Now the third step is you need to check the sign bit of A. If sign bit is 1, you need to keep that Q0 bit is 0. I have written that Q0 bit as 0. Then you need to add m. Okay, so I have added m to restore. So 1 plus 1, 10, 0 here, 1 here. So it is 11, 111, 1 here, 1. It is 10, 1 plus 1, 10, 0 here. Again carry 1, 1 plus 1, 10, 0 here. Carry 1, 1 plus 1, 10, 0 here. I ignore the carry. So now it is, I go to the previous value of A, right? That is restore, right? Go to the store the previous value of A. Okay. Now the cycle 2 is over. Repeat that steps again. Again do the shift operation. Okay, this 0 comes here. This one here. Okay. Discard this. Okay. After shifting, what you need to do? Again, 2's subtract m, that is 2's complement of m I am adding. This is the 2's complement of m. I have done the addition operation. After performing the addition operation, what I need to do? The third step is I need to check the sign bit or MSB bit of A. If the MSB bit of A is 0, if it is not 1, if it is 0, you need to set Q0 as 1 and no need to perform the restore operation. Okay, that is important. If it is 1, you need to keep the Q0 bit as 0 and perform the restore operation. But if the MSB bit is of A, that is sign bit of A is 0, keep that Q0 bit as 1 and no need to do the restore operation. Okay, now this is the A1. So this is over. Okay, the cycle is over. Now what is the next cycle? Again you need to do the shift operation. So shift come, this will come here. Okay, this Q, all those things. Okay, as it is. Then perform the subtraction, that is addition of M, 2's complement of M. I am doing the addition. Okay. Now after a complete, I need to check the sign bit of A. If the sign bit of A is 1, what you need to do? You need to set Q0 as 0. Then you need to perform the restore operation. So restore operation come. So you can keep the previous value of A or you need to add M. As you have subtracted, now you need to add M. So adding M, so I get this result. So this, after performing all the 4 cycles, it is equivalent to number of bit in the number of cycles is equal to number of bit in the dividend. Okay. Now the register Q having the quotient value, the register A having the remainder value. Check here. There the quotient is 1 0, the remainder is also 1 0. Okay. So the register in the last, the register A having the remainder value, the register Q having the quotient value. Initially the register A is initialized as 0. The Q is having the dividend value. Okay. So now this is the remainder and the Q is having the quotient. Okay. This is non-restoring division. But the disadvantage here is every time depends on the sign bit we are again performing the restore operation. It is a time taking process. Okay, so to avoid this, we are having the one more technique called non-restoring division. In the next video, we will discuss that. Thank you.